Okay, and now I am live. Hi guys. Yes, okay, now I see how it's supposed to look. um, so today we are going to do structure 1.4 for IB. It's moles, and this is one of the most requested topics for the coming mocks. If you've already had mocks, well then you still need to know this for the real exam, right? Okay, so I think we'll just dive into it because I spent like 5 minutes talking to you when I wasn't live. I don't know what's wrong with my with my technology, but I can't seem to go live from the first attempt. I just can't. Right, I'm a bit shaky because I just had a driving lesson and it was, let's say, I'm just happy I'm at home now. And at my computer, at least I'm safe and secure. Okay, so let's just dive into it. The minimum program that I want to do is I want to explain at least how to count the number of atoms in different molecules and ionic compounds, and I want to discuss combustion analysis questions. The rest, let's see how much time we have. Maybe we can also do some other things like empirical formula and stuff. So let's just dive into it. So structure 1.4 IB. Right. And let's start quickly with the moles, not the definition, but like just to understand what that means, right? So you can think about a mole as the counting number. So just like a pair means 2, a dozen means 12, and a mole means 6 times 10 to 23rd. You can have a mole of anything, a mole of, I don't know, molecules, atoms, apples, whatever. Yeah, that's just a counting number. And for example, if they ask how many molecules are there in 1 mole of H2O, you know that 1 mole is just 6 times 6.02 times 10 to the 23rd molecules. 10 to the 23rd. It's like 1 times 6.02 times 10 to the 23rd. And if it's 2 moles molecules, well, guess what? It's twice more, right? So it's 2 times 6.02 times 10 to 23rd. Now you can use a calculator for IB, so don't use your mental math anymore unless you need it for some other purposes, but not in chemistry. Well, and so on, right? That's pretty straightforward. Next, of course, that's not the exam style question. This would be the exam style question. So, for example, they could ask, we have 2 moles of H2SO4, and we need to calculate how many atoms of each element we have there, right? So if you have 2 moles of H2SO4 molecules, it means that you have 2, you see this blue 2, it's number of moles, times 2, so 4 moles of hydrogen atoms. All right, so it's 4 moles of hydrogen atoms. And if you want to find the number of hydrogen atoms, like if you count them, it would be 4, because you know that a mole is 10 times 10 to 23rd, so it would be 4 times Avogadro's constant. Yes, 6 times 10 to 23rd. So that's how many hydrogen atoms you have. For sulfur, first we find moles of sulfur. So it's 2 moles times 1. Yeah, because there is 1 sulfur if nothing is written. So we have 2 moles of sulfur. And if we need to find the number of atoms, we do 2 times Avogadro's constant. That's how many sulfur atoms we have. For oxygen, it's number of moles of oxygen is 2 times 4, yeah, so 8 moles. And if they ask how many atoms of oxygen we have, it would be 8 times 6 times 10 to 23rd, so that many oxygen atoms. Okay, now exam style questions. What's the total number of carbon atoms in 0.2 moles of glucose? 0.2 moles of glucose, that's the formula. First, carefully check what do they ask. Do they ask the moles of atoms or the number of atoms? Well, they ask about the number of atoms. There is no word moles there, right? So, okay, so first we still need to find the mole. So we do 0.2 times carbon atoms times 6. This would be the moles of atoms, but we need the number of atoms. So then I do times Avogadro's constant. Okay, so I'll be using my mental math here, so I think it's C, but okay, I won't use my mental math here. 0.2 times 6, yeah, 7.2 times 10 to the 23rd. Okay, number of carbon atoms. Then what's the total number of oxygen atoms in 1.5 moles of Na2CO3? So what do we need? We need the number of atoms, not the moles of atoms, so it's not D, at least. Yeah, if you're guessing, well, D is too small. D looks more like a moles of oxygen atoms. And then we do 1.5 times oxygen 3 times 6.02 times 10 to the 23rd. And that is looks like C. Okay. Now sometimes the questions get a bit tricky. For example, this one, what is the total number of ions? So you have to understand what particles do you, like how many particles that they ask you have in your formula. So we need the total number of ions. So it's definitely not C, not D, right? Because it's not moles of iron. So if you're guessing, guess between A and B. But then total number of ions. Okay, so how many ions do we have? This is done in structure 2. Structure 2 bonding. So if you've done structure 2, you would know that you have that NH4 plus is an ion, CO3 2 minus is an ion. So here we have two NH4 plus ions and one CO3 2 minus ion. So in total we have 3 ions in one formula. Okay, 3 ions in one formula. So you do 0.50 times 3, yeah, the total number of ions, that's moles of ions, and times Avogadro's constant. 0.5 times 3 times 602 times 10 to the 23rd, which is 9.03 times 10 to the 23rd. Fine. Okay, one more. Maybe one more. Okay, let's do one more. What's the total number of moles? Well, finally they ask for moles, right? Since they ask what is the total number of moles of atoms in 0.01 of that. So since it's moles of atoms, it can be A, can be B. This looks like the total number of atoms. And then, okay, moles of atoms. So we need to count how many atoms we have in one formula. How many atoms do we have in one formula? Well, we have one platinum, one Pt, two nitrogens, 3 times 2, 6 hydrogens, and 2 Cls. That's 11. So the total number of moles of atoms would be 0.01 times 11, which is D, 0.110. Fine. Okay, I think it's fine. I think you caught the idea. Right, then moles relative atomic mass relative formula mass. The definitions you need to know, I just leave it here. You can read it, you can screenshot, you can pause and read it. I'm not going to read them. Just remember you need to have the words relative to something, yeah, because that's relative, molecular relative atomic mass. So just pay attention to the word relative to what you're measuring it. Right. I think everyone knows how to calculate relative molecular mass. I'll show it for maybe two substances and then we move on. So that's not an exam style question, obviously. That's just a well, just like a practice problem. So calculate MR of the MR is relative molecular mass or formula mass of the following compounds to 2 decimal places. Okay, the thing with IB is that for paper 2 you always have to calculate MR to 2 decimal places, how it's in the data booklet, in the periodic table. So, okay, so let's do it. So MR of H2CO3. So what do? We do 2 hydrogens, 2 times 1.01, yeah, relative atomic mass, plus 1 carbon, 12.01, plus 3 oxygens, 3 times 16. And whatever that is, it's relative molecular mass of H2CO3. Plus 12.01 plus 3 times 16, so 62.03. And then let's take something like Al2SO43. Okay, let's do that. So I have 2 aluminium, so 2 times aluminium is here 26.98 plus 3 sulfurs, yeah, because this 3, it refers to both sulfur and oxygen. 3 times sulfur, 3207, and plus 3 times 4, it's 12 oxygens. 16. 2 times 2698 plus 3 times 32.07 plus 12 times 16, which is 342.17. So that's how we're finding MR. Next, these two formulas are the most important ones in the whole syllabus. So moles, it's mass divided by molar mass. Mass is moles times molar mass, right? So you need to know how to rearrange them. Again, I think it's fine. You can, well, maybe let's practice one question. So, for example, how many moles are there in 16 grams of H2O? So you have grams. Grams is always mass. So this is mass, and you need to find moles. And so you're using the first formula. So N would equal to mass over M. M is the same as MR, but with the units. That's why there is no relative yet. It's gram per mole. But you calculate it in exactly the same way as we just did. So you do 16 divided by H2O, right? So it's 2 times molar mass of hydrogen plus 16. And then whatever that number is, that's your moles. 1 plus 16, 18.02. And then you do 16 over 18.02, 0.888 moles. Right. How many grams are there in 1.25 moles of CO2? So you need to use this formula, right? Because you want grams, you want to find grams. That's mass. And so you're using the formula M equals to N times molar mass. So you do 125 times molar mass of CO2, 1 carbon, carbon, remember 12.01, plus 2 oxygens. 16 is from the periodic table. Times 125, so 55 grams. Okay, that's fine. Right, next, empirical and molecular formula. Let's see, do we have time? Yes, let's do this. I think we can do it. So empirical formula shows the simplest whole number ratio of elements in a compound, and molecular formula shows the total number of each element in a molecular compound. For example, if C2H4 is a molecular formula, so what does it show? It shows that your molecule has 2 carbon atoms, 4 hydrogen atoms. And to find the empirical formula for this molecular, what you need to do is you need to cancel the indices out by some number to get the smallest possible number. So you can cancel them out by 2, right? So you can divide 2 and 4 by 2, and so you'd get 1 and 2. 1 you don't have to write, so CH2 is the empirical formula. For C4H10, again, you can divide both numbers by 2, so it would be C2H5 is the empirical. If C4H10O is molecular formula, there's nothing you can do with this oxygen. It's 1, right? So it just stays as C4H10O for the molecular formula, for the empirical formula. So both molecular and empirical in this case would be the same. A few more examples. So deduce the empirical formulas for the following compounds. C3H8. I'm checking, can I cancel 3 and 6 by some number? Well, I can cancel them out by 3, so 3 divided by 3 is 1, so C1. H, 6 divided by 3 is 2, CH2. C6H12O6. You can divide it by 6, right? So it would be C1, H2O1, and so on. For example, C5H12, there is nothing I can do about it. It just stays as C5H12 because there is no other number by which I can divide to get a whole number in both cases, for both C and H. Right, and then next type of questions. So let's solve this type of question. It's when you are given either masses or percentage by mass of elements in some compound, and you're asked to find empirical and sometimes molecular formula. This is a very good type of questions because usually these questions are 4 marks and they're very predictable, so nothing can go wrong there. You always do it in the same way and it works every time, so just pay attention. I think it's like 3-4 marks in the exam if you get this question. Well, I mean this type of question. Right, let's see. So this is an example. Glucose contains 40% by mass of carbon, 6.67 of hydrogen, and 53.3 oxygen. MR of glucose is 180. Calculate the empirical and molecular formulas of glucose. Okay, so we need both empirical and molecular. We always start by finding, I know I'm blocking the view, right? Okay, so I'm starting by finding empirical formula. And that's what we'll do. So it doesn't matter whether they give you percentage by mass or masses of elements, because we can just say, if they give percentage, we can just say, let's assume we have 100 grams of the substance, right? So we can do, I'm still blocking the view, so there is nothing I can do about it. So I'll just trust me, there is 53.3%. Okay, so what I do is first I find empirical formula. Empirical formula. So we take the percentage for each element. So carbon is 40, hydrogen is 6.67, oxygen 53.3, and we divide it by relative atomic mass. So if you haven't memorized it yet, I highly recommend to memorize it because it will save you time. So carbon 12.01. So I'm kind of converting masses to moles, right? Because in the empirical formula, I have the ratio of moles of atoms. Hydrogen 1.01, oxygen 16. And then calculate. That's 3.33. 667 over 101 is 6.60. 53.3 over 16, 3.33. Right, so we got some numbers. Obviously, these are not whole numbers. And what do we like? We like whole numbers. To get whole numbers, the first thing that you could do is you can divide all of the numbers by the smallest. So by 3.33. So you get 1. 6.6 over 3.33 is 1.98. That's close enough to 2. So 2, 1. Right, we got our whole numbers. And it means that our empirical formula would be C1H2O1, right? So CH2O. That's our empirical formula. Okay, now molecular formula. To find the molecular formula, we need to find out how much heavier is our true formula, which is molecular formula, compared to the empirical formula, right? To do that, what do we do? To do that, we need to find molar mass of the empirical formula. So 12.01, that's 1 carbon. 2 times 1.01, that's hydrogen, and 16 is oxygen. That's what, 30.03, right? 30.03. Okay, and then we divide. Yes, so then we divide. So I know that my MR, real MR, is 180, empirical is 30, so I do 180 over 30.03. And here you have to get the whole number. Well, of course, this one would be what would it be? It would be like 5.99, which is 6. Yeah, that's close enough to 6. If you get some weird number like 6.2, well, something is wrong. Yeah, so then you have to double check everything. So maybe you did something wrong. Okay, so we got a whole number. It must be a whole number at this point, and then you just have to multiply all the indices by 6. Yeah, so instead of C1H2O1, you get C6H2 times 6, 12O6. That's the molecular formula. Okay, done. These ratios might not always be that nice, right? So just make sure that you don't round the numbers too quickly, right? So you could get some other ratios. Let's say if you get if at this point you get a ratio of 1 to 1.5, well, 1.5, it's not 2 and it's not 1, so you just have to keep it and then multiply all the numbers by 2. So you get, it's the same as 2 to 3. If you get a 1 to, let's say, 1.33, 1.33 is too far away from 1, so you cannot round it to 1. You have to multiply by some whole number. So you try to multiply by 2, does not work. You won't get whole numbers. If you multiply by 3, well, I think it would work. You would get 3 to 4, right? And then if you get 1 to 1.25, again, 125, it's too far away from 1. So you multiply both by 1 does, by 2 does not work, by 3 does not work, by 4. By 4, yeah, 125 times 4 is 5. So it's 4 to 5. 4 to 5. Okay, so careful when the numbers are not as good as I got in this question. All right, next. These I'm skipping, that's similar questions. Right, and this is the last thing from my minimum program that I wanted to cover. It's analysis of combustion data. And actually, let's just do a more complicated question, this one. I'll see if am I covering? It just updates, so okay, I'll just leave it like that, but I'll read it out. So com combustion analysis question 1.4 still, yeah, IB. Right, so this is how it goes. 0.255 grams of an organic compound completely burns in oxygen to produce 0.561 grams of CO2 and 0.306 grams of H2O. Determine its empirical formula. So you have to recognize this type of questions. You are asked about empirical formula, but not like before, right? So before, in the question that we just solved, you were given the percentages or masses of elements of each. I mean, like what is the mass or percentage of each element in a compound. Now here you don't have that, but instead they're burning. Yeah, so they're burning a compound in excess of oxygen, and they get CO2 and H2O. Yeah, so some products. And the most important part to understand here is, well, let's say you're burning some compound. We have no idea what's the formula, that's what we have to figure out. It could have oxygen, or it's possible that it doesn't have oxygen. Because they didn't say. We know that the only products are CO2 and H2O, which means that it definitely has carbon, it definitely has hydrogen, possibly oxygen. That we don't know, we have to check. And when you combust an organic compound in excess of oxygen, you get always CO2 and H2O. Right. Then we need to understand that all the carbon from this compound, it was transferred to CO2, right? So all the carbon atoms that were here after the reaction, they are in the CO2 molecules. All the hydrogen is now in H2O molecules. For oxygen, we cannot say that, right? We cannot say that all oxygen was transferred to CO2 and H2O. Why? Well, because we've added some, right? And we don't know how much. So for oxygen, we have to figure it out somehow differently, how much was there, and if it even was there. Fine. So to find the empirical formula, my goal is to find the moles of atoms of carbon, the moles of atoms of hydrogen, and the moles of atoms of oxygen here in the CXHYOZ, and then take the ratio, and the ratio would show me the indices. All right. Fine. Let's do it. How do we find the number of moles of carbon? Well, from CO2. I highly recommend to memorize the steps, or at least to understand them in such a way that you don't have to figure it out in the exam, because it will take you ages. So I do moles of CO2. We know the formula for moles. It's mass over mR. Okay, so we have 0.561 divided by mR of CO2. I have to just scroll up. So 12.01 plus 2 times 16. That's 0.561 over 44.01. 0 1 40. And then, okay, and then each molecule of CO2 has one carbon atom, so I can find the moles of carbon. You see, it's 1 to 1. Yes, so one CO2 molecule has one carbon atom, so the moles of carbon would equal to the moles of CO2. I will highlight this ratio because, I mean, this value, because we would need it for the final ratio. Then I do the same for hydrogen. How can I find hydrogen? Well, from water. So I find the moles of water that was formed. It is 0.306 over mR. So that's 0.306 over 18.02. 001, what is it, 70 moles. That's moles of water, and each water molecule has two H's. Now I find the moles of hydrogen. The moles of hydrogen atoms would be twice as much, right? That's what we talked about in the very beginning, because each water molecule has two H atoms. So I do 2 times moles. This value I would need for the final ratio. Okay, fine. Now what do we do with oxygen? So with oxygen, we, as I said, we cannot apply the same logic, right? Because we've added extra oxygen. But what do we know? We know the total mass of the organic compound. So what is this total mass? This total mass, it's mass of carbon atoms plus mass of hydrogen atoms plus mass of oxygen atoms, because there can't be anything else. So what I will do is I will find the mass of carbon atoms, the mass of hydrogen atoms, and then I would subtract 0.255 minus the mass of the carbon and hydrogen atoms. And then if something is left, that something must be oxygen. If nothing is left, then there is no oxygen. Well, let's see. So I find the mass of carbon atoms. It's moles times relative atomic mass here. So times 12.01. 168 grams. Then mass of hydrogen, it is hydrogen, where's hydrogen? 0.304, right? These moles. So moles times relative atomic mass, which is 0.0343 grams, and then mass of oxygen. So I do my total mass, which is 0.255. Oh wait, why is this so big? Over 44.01. Oh, I did this one wrong. Hold on. This is not this number. Yeah, wrong number. But I could see it right away, because you see I got the mass that was higher than what's the total mass. So I just calculated this number on. So it's 0.561 divided by 44.01, which is 0.0127. Yeah, so that's 0.0127 moles. That's the number that I would need. So this is wrong. This must be 0.0127 times 12.01, which is 0.1525. Well, 153. Okay, and then mass of oxygen would be 0.255, or I hope I haven't messed up anywhere else. I will double check. Okay, but actually at the end I would see, yeah, if the ratio is wrong, I would see that I made a mistake somewhere. If the ratio doesn't give me the whole numbers. Okay, so so that's the total mass. I do total mass minus mass of carbon atoms minus mass of hydrogen atoms. Okay. Which is 0.0677 grams. All right, let me just double check real quick. So, okay, so we had 0.561 over approximately 44, right? I'm just quickly checking. Yes, and that's correct. And then 0.306, yes, and divided by 18. 0.017 times 2, 0. Yeah, looks right. Okay. Looks right. And then 0.0127 times 1201. Yes, and that's right. Okay. Now I will convert the mass of oxygen into moles. That's the final thing I need for the ratio. So 0.0677 divided by 16, which is 0.00423 moles. Right, that's the final thing. And now we will see if we messed up somewhere. So now I take the ratio of carbon atoms to hydrogen atoms to oxygen atoms. 0.0127 to 0.0340 to 0.00423, dividing by the smallest number. Right, I'm dividing it by the small. I hope I'm still live. Am I live? Why does it show? Oh no. Okay. I'm not sure if I'm live, but I will finish this question just yes, I don't know. 0 0 2. Okay, so I'm dividing all the numbers by the smallest, so by this one. 0.0127 over that. Okay, yes, it's 3. Whole number. Whole numbers, we like whole numbers, right? 3. 0.034 over 0.00423 is 8. And this is 1. Yay. Okay, so it means that we haven't messed up. I haven't. I haven't. And so it means that you have 3 C's, 8 H's, and 1 O. So it's C3H8O. That's the empirical formula. Empirical formula. Right. Well, that's it. Yes, they didn't ask us to find molecular formula, and we cannot find the molecular formula because they haven't given us the molar mass. And I know that this is probably an alcohol, so it's the molecular formula as well, but that you don't have to think about it just yet. Right, so that's the question type. So let's just quickly recap, and I think I will let everyone go. So we haven't covered the entire 1.4, but I don't have time anymore. So let's recap. So, okay, so this is the type of questions when you're combusting a compound and you know the mass of the organic compound, you know the amount of CO2 formed, the mass of CO2 formed, and you know the mass of water. So you do moles of CO2, and that equals to the moles of carbon. Then you find moles of water, and that equals to, and then multiply it by 2, that equals to the moles of hydrogens. Remember the 2. Then you find the mass of carbon and hydrogen and do total mass of the compound minus mass of carbon atoms minus mass of hydrogen atoms. So you get mass of oxygen. Then you convert that into moles, and then you take the ratio of moles of C, H, and O. Okay, right. Well, I hope that was helpful. The next stream, I'm thinking to start organic chemistry for A level, but we'll see. So if you have any requests, as always, you feel free to send me a message and I'll see what I can do. All right, so see you next time.